All right, this is a short video just to talk through some of the important points from the WestobyPaper that you read this week. Um, so here's just a few images that are cross sections of different leaves. So this is always helpful for me to kind of think about what's going on inside a leaf as I think about what leaf mass area is telling us about leaves and plant strategies. So just remember we've got a couple of epidermal layers on the leaf, and then all of this stuff in between is the mesophyll. This round area here is the bundle sheath. Down in this image here, this is another nice one. You can see this large bundle sheath here, this kind of gray area. There's a smaller bundle sheath that's over here. And on this one, it's kind of nice. You can see all of these big air cavities, which is part of the spongy mesophyll. If we go back up to this upper image, you can see there's very little of the spongy mesophyll, and so very few air spaces. So this plant here, I would expect to have higher density of cells than this plant down here. And remember, the two things that are controlling LMA, or controlling differences in LMA, are leaf density and leaf thickness. So these two might differ in leaf density. Okay, let's talk about the WestobyPaper briefly. So in the WestobyPaper, he talked about the dimensions of variability, or just the variability in how plants are behaving and the large number of species that exist. And so in order to take that very large number of species and somehow say something about how all of those species might behave or respond to different conditions, we can't go out and measure those responses on everything. That just takes way too much time. For example, Bouteloute gracilis, or blue grama, which is the dominant species in the shortgrass steppe east of town here, people have been studying the physiology of this species like for 50 years or more, and there's still a lot we don't understand. And so if you then multiply that by all of the species on Earth, we just don't have the time to do that. So Westoby's idea, and many other ecologists, is how can we somehow simplify or identify something simple to measure that would describe those physiological responses. So he talks a little bit about Grimes' theory, or way of categorizing plants into either a competitive, a stress tolerator, or ruderal species, which that did a lot to move us forward in ecology, but that's like putting all of the plants in three categories. So we can do better is Westoby's idea, or at least his motivation for looking into this leaf mass area trait a little bit more. Oops, didn't mean to do that. So we're looking for ways to measure something easy but tells us about the growth strategy of plants. And so this would be a plant trait, and Westoby talks a bit about some of those criteria that we might use to identify plant traits. But one of the traits that meets those criteria is leaf mass area, or specific leaf area. So leaf mass area is grams of dry biomass divided by meters squared of hydrated leaf area. Specific leaf area is just the inverse of that. It's leaf area divided by biomass. Remember that the two things that are driving differences between species in LMA is either the thickness of the leaves or the density of the leaves. Not leaf size, it's only thickness and density. And what high LMA means is that leaves are requiring more investment in the construction of those tissues when building the leaves. So if a plant has leaves with high LMA, it means that plant invested a lot in constructing each individual leaf. But high LMA leads to leaves that typically are tougher, so they can handle greater wear and tear, and they're more resistant to herbivory. And so that means they can stay on the plant longer, and the plant can use that investment for a longer period of time. So the way he captures that idea is with this graph that is in the paper. So I'm just going to walk through this, and then we're going to look at an example of two leaves, one that would have a high LMA and one low LMA. So the x-axis on this figure is time since the leaf was constructed. So here the leaf, it doesn't exist, and then, or it's at the very beginning of when it was constructed. And then this is over the course of its life. And then on the y-axis, we have the cumulative net return per unit leaf area. So it's the net gain of carbon, essentially. So this curve here is representing a particular leaf. At the beginning of its life, when it's first constructed, it has a negative net cumulative gain because it hasn't actually gained and added carbon back to the plant. It's kind of in debt to the plant, right? So the plant invested this carbon, and so it's at a net loss right now of carbon after it constructed that leaf. But as that leaf photosynthesizes and adds carbon to the plant, the net gain approaches zero, and then when it crosses zero, you know, that's a really important part of the plant's life, like celebration, yay. But if a plant doesn't make it to point A, then that was a bad investment on the plant's part, right? It wants it to at least get to A to pay back the carbon, and then hopefully go beyond A so that the plant gets much more carbon than what it invested in that particular leaf. So you can see this initial slope here is relatively steep. So the rate of return is relatively fast, but at some point that begins to slow, and that's where point B is. Boy, I'm sorry, like my mouse is super sensitive today. This isn't the computer I usually use. So when that rate starts to slow is at point B, and that's about when we think of a leaf as reaching its optimal lifespan. Because after that point, it's not adding a lot of new carbon back to the plant. At point B, like maybe it adds a little bit more carbon, but at some point it's going to become a carbon sink, or like other leaves are going to have to support that leaf and add carbon to the plant. So this is a point where we would expect a leaf to be senesced from the tree is around this particular point. And C is where this curve plateaus. And at this point, that leaf is no longer adding new carbon to the tree. And at some point, it's actually going to become, you know, kind of a burden to the tree, because the carbon from the other leaves is going to have to go to fund the baseline metabolism of that leaf. And so other leaves are actually kind of propping it up and supporting it. So that's a time when a leaf shouldn't really be existing on a tree anymore. Okay. So let's now compare two different leaves. So this black line here represents the leaf we were just looking at. And then I've drawn this new kind of orangish line here on the figure. So let's look over here at the y-axis, or the y-intercept, sorry. And we can first see that this orange line is further down on the y-axis. It means it's basically further in debt to the plant. This leaf is the orange, we'll call this the orange leaf and the black leaf. The orange leaf is in more debt than the black leaf is. Or another way of thinking about it is the plant had to invest more carbon in making this orange leaf. So we would expect this orange leaf to have a higher LMA because it's more in debt, or the tree invested more carbon in it. First thing we can see about these, where we're comparing these two lines, I guess that's the first thing we can see. The next thing we can see is that these initial slopes are different. I probably should have accentuated these differences a bit, but hopefully you can see the point I'm making. The leaf that has higher investment in it has its initial slope is lower than this leaf with less investment. And what this is representing is the fact that plants with high LMA tend to have lower photosynthetic rates. So it's still paying back its carbon to the plant, but it's doing it at a slower rate than this leaf with low LMA. So what that means is it takes longer for it to cross that y-intercept and pay back all its carbon. But remember, a leaf with higher LMA tends to be tougher and have greater wear and tear, and so it stays on the tree longer. So So this leaf with higher LMA, even though it takes longer to pay back its carbon, it can keep doing that for a longer period of time before it actually slows down, and then a plant might consider senescing that leaf. So slower payback, but over a longer period of time. And so these two strategies of, so now if we back up to thinking about a plant constructing either high LMA leaves or low LMA leaves, those two different strategies have advantages under different conditions. And we'll talk more about that. Westoby talks a bit about that. I'll just say a couple things now. Typically, we think of this plant with low LMA leaves and these high carbon payback rates. Those are in places where resources are pretty plentiful. So in those cases, like having it's kind of the live fast, die young idea. Like you don't put a lot in your leaves, it's going to photosynthesize really quickly, but then you're going to senesce it pretty fast. That works fine when like you can easily build a new leaf. You've got plenty of nitrogen, plenty of water, so you can continue to grow really easily. Building cheap leaves is okay in that situation and tends to be an advantage because you can turn over your leaves really quickly. A plant with high LMA, they tend to do well in places that have harsher conditions for plant growth, low nutrients, low water availability, because they're not going to grow fast anyway because those resources aren't available. But being able to hang on to those leaves for a long period of time and even for multiple years, that becomes an advantage because it doesn't have to reinvest carbon every year to build leaves. It can reuse that same leaf, reuse those same nutrients over and over again. And over the long haul, it's able to accumulate a lot of carbon. So just a little insight into what those different strategies might look like from a plant's perspective. All right, when we do this in class, I have you kind of write this out in your own words. We'll skip that for now. But I want to talk about a couple of the important relationships between LMA and kind of leaf function or in plant strategies, because these are essentially some of the variables we're looking at in this assignment 7. So this first figure here shows LMA on the x-axis and leaf lifespan in months on the y-axis. So leaf lifespan is how long does that leaf stay on a tree. So we can see this relationship, positive relationship between LMA and leaf lifespan. So as we move to the right on the x-axis, these leaves towards the right have higher and higher LMA. So that means they're thicker and or more dense leaves. They have greater wear and tear, so they're going to stay on the tree longer. And that you can see that in the longer leaf lifespan. And so these leaves out here on the far right of the figure, they're lasting for multiple years on the tree. And this data set comes from a couple hundred different species all around the globe. So it's a really big data set. Okay, so that same figure is shown here on the left, but it's shown to contrast it with this trade-off associated with growth rate that I've already talked about. LMA is again on the x-axis, and then we have photosynthesis on the y-axis. And you can see that plants that have high LMA, they've invested a lot in the structure of their leaves, they tend to have lower photosynthetic rates or lower growth rates. So if we go back to this figure right here, we can see that conceptually, right? This orange line represents the plant with high LMA, and it has slower returns on the investment from the plant. So this represents lower photosynthetic rates. And the reason for that is if a plant takes a lot of the resources and invests it in the structure of the leaf, there's fewer resources left over to do all of the physiology. And so a plant that's investing in the structure has less to do with the physiology, and then vice versa, a plant that invests very little in the structure of its leaves, it can invest more in all of the physiology and the actual action of the leaves. And that's part of the reason we see this really strong trade-off between LMA and leaf photosynthesis. Okay, so these first 4 major bullet points are from earlier in the slide, and then I just added this one, that plants that are successful in stressful environments tend to construct leaves with high LMA. And I already mentioned that, but that's kind of the the trend we generally see. Okay, that's all I've got for reviewing some of the important parts of the Westoby paper. I put this in the assignment description for assignment 7, but you do need to reference the Westoby paper in your assignment, in your lab report. So you could do that. A good way to do it is in the introduction when you're talking about what LMA is and kind of defining it. You could cite the Westoby paper, or you could cite it in the discussion section as well, or both, whatever you decide.